In this work, we investigate and analyze a range of optimizations for NPM simulations on GPU platforms. We identify algorithmic design choices and data structures that facilitate high-performance simulations on modern graphics hardware platforms. Our proposed techniques enable efficient simulation of a large variety of complex materials, which can yield visually rich animations and computer graphics tasks. Here we summarize our contributions. We propose a novel GPU scheme for the efficient transfer of data from particles to grids based on a scattering paradigm. We conduct a thorough analysis using a collection of experimental benchmarks to evaluate our algorithm against alternative implementation approaches. In addition, we design an NPM-based implicit heat solver that simulates thermomechanical effects on elastoplasticity. Finally, we present an easy-to-implement unilateral hyperelasticity model for cohesionless granular media. To build the mapping from NPM particles to the background grid, we divide the Cartesian domain into blocks, such as the 4x4 block illustrated here. Particles are similarly partitioned into groups, each corresponding to one of the grid blocks. Consider the 4x4 block of cells in the dual grid shown in red in this illustration, which is offset by a half cell from the original block. Any particles that reside in the dual red block are assigned to the original 4x4 block in our grid. We store grid data for each block using our proposed GPU variant of the SP grid structure, or GSP grid. We assign each GSP grid and its corresponding particles to one CUDA block. Notice that the particles within one block can also exchange data with grid nodes from 3 neighboring blocks in 2D or 7 blocks in 3D respectively. We resolve this problem by utilizing the shared memory in each CUDA block. We associate each particle with one CUDA thread, and as a result, each CUDA block will handle hundreds of particles, which makes it justifiable to allocate enough space for all neighboring 8 blocks. We exploit modern warp-level CUDA intrinsics to resolve the write hazards in the traditional scattering scheme. Assume we have 8 particles in a warp, and they are writing their weighted mass into nodes from node n to node n+3. We first mark all boundary particles whose neighboring particles are writing into a different node, and compute the corresponding interval for each of them. Then we can iteratively shuffle the weighted mass from right to left. Finally, boundary particles will be responsible for writing the sum. Plasticity in NPM is usually attained explicitly, or lagged, in implicit schemes. In the work by Clar et al., lagged plasticity causes severe numerical cohesion. Tempubulan et al. Presented a complex unilateral extension of the elasticity. Their model requires 3 additional parameters for behavior tuning and causes sand to spread unnaturally even in a simple column collapse test. Our model, on the other hand, does not require any additional parameters. Here we show a comparison result for explicit NPM. For implicit integration with lagged plasticity, our unilateral model closely resembles the characteristic shape of the original Drucker-Prager behavior without suffering from overly spreading artifacts and unnatural wavy patterns. Here we show more 3D results simulated within our framework.